Hello viewers, welcome you all. Today we are going to discuss heat treatment process, which we are using in the industries to enhance the mechanical properties of the material, to alter the mechanical properties of the materials. So, in the heat treatment process, we are using heat for treating the material, altering the material properties, to enhance the mechanical properties of the material. So, welcome you all. I am Sunil Kumar Ojha, Assistant Professor in Department of Mechanical Engineering, IIMT College of Engineering, Greater Noida. So, what is heat treatment? If we have to go to change the mechanical properties of the material, uh, as defined, uh, heat treatment is a controlled heating and cooling of the metals for primary purpose of altering their properties like strength, ductility, hardness, toughness, machinability. So if you have to see, there is a in the axis, there is a temperature and there is a time. So if we have to heat the material, then hold it for particular time, and there is a different cooling rate. Then we have to change the properties of the material, like as in the definition: strength, ductility, hardness, toughness, and machinability. So variation of temperature and time by heating and cooling, we can change the properties of the material. So this is the simple definition of the heat treatment process. So why we are going to do this process? The purpose of this process is to, as in you can see, relieve the internal stresses. So we have to. There is a internal stresses stored in the material which can harm during the operations use of the product parts. So we have to relieve that internal stresses. So we have to use heat treatment process to improve the machinability. So material machinability is nothing but how we have to ease the easy machining process we have to do. So that is how we have to improve the machinability of the metals. To refine the grain sizes and to soften the material, like we have to improve the ductility of the material, to improve the hardness of the material, how hard we have to make the material by this process, to improve the mechanical properties, various other mechanical properties of the material, to increase the resistance to wear when there is a product parts we are using, where there is a more wear rate. So we can how we have to increase the resistance to wear, heating, and corrosion, to improve the ductility and toughness, and to change the chemical composition of the material. So all these things we can, all these purposes we can do the heat treatment processes. The purpose and objective of this heat treatment process. So who uses heat treating? So heat treatment is used in various industries, vastly used in the industries, in the aircraft industry, parts we are making, that is heat treated, automobile manufacturing industries, defense sector, forging, foundry, heavy machinery manufacturing, powder metal industries. So all various sectors in the parts products we are using heat treatment process to change the mechanical properties of the material. So what are the steps involved in the heat treatment operations? As you can see, first we have to do loading. So what we have to do in the loading? First we have to clean the material, pre-wash with coalescence, dephosphate system, spray rinse. So first we have to clean the material. Then heating, we have to do the heating. Heating the material, first we have to preheat the material. Then we have to heat properly up to desired temperature. Hold at that time soaking, that is called soaking, and diffusion, so that that material properties get enough time to change their properties, and pre-cooling. Then we have to doing as per required cooling rate, that is if you have to do quenching or post washing and tempering, surface coating, etc. And then we have to unload the material. So this is all steps. These are the steps involved in the heat treatment operations. Next, steps in the heat treatment, uh, as we have seen, required there are three basic steps. As we know, heating of the material to the specific desired temperature. Holding means that is called soaking at that temperature, that fixed particular temperature for appropriate time. Cooling according to the prescribed method means what are the cooling rate required for changing different properties. So heating temperature range up to 2400 degree Fahrenheit or 1316 degrees centigrade, like this for steel material. Soaking time vary from few seconds to 3-4 days, means holding time. And cooling way may be slowly in the furnace or quickly quenched. These are the some different cooling rates. Into the water, brine solutions, polymer solutions, molten salts, molten metals or gases. 90% of the metal parts are quenched in the water, oil, polymers or gases. So these are the steps in the heat treatment. There are three basic steps: heating, holding or soaking, and cooling different rates as per requirement. So here there are various types of heat treatment processes. As you can see here in the presentation: annealing process, normalizing process, hardening and tempering process, case hardening process. Annealing process further having three different steps, three different types of annealing: full annealing, stress relief annealing, spheroidizing. Then normalizing process, heat treatment process, then hardening and tempering process. That is further there is three different types of hardening and tempering: conventional hardening and tempering, harsh tempering, and mar tempering. Then there is a case hardening, that is also called differential hardening, in which carburizing, cyaniding, nitriding, and carbonitriding. Then flame hardening, induction hardening, electron beam hardening, laser beam hardening. So these are the different types of heat treatment processes. So first we have to discuss about the annealing process. So annealing is nothing but it refers to heat treatment process in which the material is exposed to an elevated temperature for an extended time period and then slowly cooled. When an annealed part is allowed to cool in the furnace, so we have to keep in the mind when we have to heat the material at the elevated temperature, and then we have to allow the material to cool inside the furnace. It is called full annealing heat treatment process. As we know, there are different types of annealing process. Annealing process is one is full annealing, then process annealing, stress relief annealing, recrystallization annealing, and spheroidizing annealing. So these are the different types of annealing processes. So full annealing objectives are to soft the material, making it more and more ductile, relieving the internal stresses in the material, and refining the grain structure. Next is how we have to in the temperature versus composition diagram, we can see what are the different compositions, and in the temperature range, particular temperature range, how we have to perform the full annealing process. So like you can see here in the graph, there is a temperature 723 degrees centigrade. That is a lower critical temperature line. 0.8% of carbon, and before that this is hypoelectric steel, and 0.8 to 1.8 or 2% up to 2%, that is hyperelectric steel. So we can perform annealing process based on the composition and temperature range, and there is a critical temperature, so we have to perform that accordingly. So how we have to do full annealing process? In the full annealing process, we have to heat the material 30 to 50 degrees centigrade above the upper critical temperature for hypoelectric steel. As you can see, this is the hypoelectric steel. below the 0.8% of carbon. We have to heat the material upper critical temperature of the 30 to 50 degrees centigrade more than the upper critical temperature. Then 30 to 50 degrees centigrade above the lower critical temperature for eutectoid steel. So if there is that is eutectoid more than 0.8% of carbon, then 30 to 50 degrees centigrade from lower critical temperature for eutectoid steel. Cooling is done at the furnace at the rate of 10 to 30 degrees centigrade per hour. So very slow rate of cooling we have to achieve, and we have to do inside the furnace. We have to switch off the furnace, and accordingly that furnace cool down. The cooling rate is normally 10 to 30 degrees centigrade per hour. For hypoelectric steel, the resulting microstructure is coarse perlite and ferrite. So after that, we have to for hypoelectric steel, we have to find the microstructure of full annealing process is coarse perlite and ferrite type. Those who know the microstructures, they can understand the coarse perlite and ferrites. For hypoelectric steel, annealing temperature is 30 to 50 degrees centigrade above the lower critical temperature. For hyperelectric steel, the resulting microstructure is coarse perlite and cementite. This process provides high ductility and toughness. As you can see here in the structure, ferritic and cementitic structure, annealed and coarse laminar perlite and medium laminar perlite, normalized medium laminar perlite. Difference in the perlitic structure due to annealing and normalizing process. Next, stress relief annealing. So, as you name suggests, we have to remove the internal stresses of the material by this annealing process. So, stress relief or recovery annealing process. It is also called recovery annealing process. Annealing temperature is at the range of 550 to 700 degrees centigrade. There is a uniform cooling is mandatory. Cooling rate should be uniform. It eliminates the stresses formed during the welding. So this process is very important in the manufacture and the processes like welding, cold working, casting, quenching, and machining process. The internal stresses stored inside the material. To remove that internal stresses, we have to use this stress relief annealing process. Next is a need for stress relief annealing. Causes of stresses. So how that stresses are caused when there is a manufacturing process like forging, forming, or plastic deformation processes during the machining. Non-uniform cooling, when there is a non-uniform cooling, that internal stresses set up inside the material. Phase transformation between phases with different densities. So these are the causes of that stresses are stored inside the material. Effect of stress, what are the effect of these internal stresses? This will cause rappage of material, cracks that will develop cracks or distortion in the material. So removing that internal stresses is very important. So we have to use stress relieving annealing. Next is recrystallization annealing. Recrystallization annealing, it is the process in which distorted grains of cold work material are placed by the strain-free new grains. Recrystallization annealing is an annealing process at temperatures above the recrystallization temperature, cold work material without phase transformation. So we have to do the recrystallization temperature is not constant for material, but depends upon the amount of cold work, the annealing time, and other factors. So recrystallization temperature we have to calculate from the melting point of the temperature. This is the equation. T recrystallization temperature is equal to 0.4 T melting point temperature of material. So as you can see in the diagram, the property and progress of recrystallization, there is a graph. Strength, hardness is reduces as the progress of recrystallization, and ductility, toughness is increases by this process by different achieving the composition or microstructure of the material. So there is a nuclear pair at the position of the high stored energy nuclei growing into the adjacent deformed grains, and the nuclei fully develop to form strain-free new grains. So this graph we can see here in the different properties. It reduces the dislocation density and converts elongated grains to equiaxis. After cold work, figure A is the after cold work, and figure B is the after recrystallization annealing. Next is spheroidized annealing. So spheroidized, something spherical in shape, circular in shape. So converts laminar perlite into globular perlite. Plates of the cementite, spheroidized of the cementite. So that is the conversion process. We have to make spheroidized or globular microstructures. So you can see here, these are the ferritic line in the, this is the microstructure. So these are the lines of the microstructure, and after the heat treatment process of spheroidizing annealing, we have to find the grains in the spherical in shape. So the main objective of why we do spheroidized annealing, to soften the steel, to increase the ductility and toughness. These are the also we have to achieve, and most important is improve the machinability and formability of the material. With the help of this spheroidizing process, we have to do easy machining, smooth machining of the metals, mostly steel. Also reduces the hardness, strength, and wear resistance. Materials mainly concentrated medium carbon steel and high carbon steel. This spheroidized annealing is not used for low carbon steels. So this is the temperature versus composition diagram, in which we can see the process of spheroidized annealing. Next is 3 ways of spheroidizing. How we have to do spheroidized annealing: prolonged heating below the lower critical temperature. We have to heat the material for a long period of time below the lower. So this 727 degrees centigrade for steel material, and below that we have to heat the material at below the lower critical temperature, and then slow cooling is we have to do. Then cycling between the temperature and then relatively slow cooling. So this is the another process. And for tool and high speed tools, heating at the temperature range between 750 degrees centigrade to 800 degrees centigrade, then hold at this temperature, and then slow cooling is we have to do. So these are the 3 different spheroidized annealing process we have to do. All these things we have to summarize in this time and temperature versus time diagram. Stress relief annealing, then process annealing for hypoactivized steel, and annealing of inside the furnace cool, isothermal transformation, and this is the normalizing process. So this is the diagram in which all the annealing processes shown here. Next heat treatment process is normalizing process. So normalizing process is nothing but when an annealed part is removed from the furnace and allowed to cool in the air, it is called normalizing process. The difference between annealing and normalizing is that in the annealing process, in the previous topic we have discussed, the cooling is done inside the furnace, and in the normalizing process, cooling is done outside the furnace in the cool air or still air. The main objective to do the normalizing process is to refine the grain structure, to remove the strains, to remove the internal stresses, to remove the dislocations in the material, to improve the mechanical properties like strength, hardness, toughness, to improve the machinability of low carbon steels. So these are the some main objectives of normalizing process. So you can see here time in the phase diagram. there is temperature and carbon percentage. So these are the diagrams showing normalizing, annealing, and sterilizing different types of processes, heat treatment process in phase diagram. Next process is hardening process. So hardening process we have to do to increase the hardness of the material. Heat treatment, which is used to produce martensite. So in the hardening of the material, our objective is the microstructure we have to obtain is martensite. Objective is to improve the hardness and improve the wear resistance. So those parts required wear resistant properties, then we have to do hardening process. So steps in the hardening process is heating, soaking, and rapidly cool the material. Completely cooling or rapidly cooling the material. So factors that affect the hardness is the carbon percentage in the steels. By increasing the carbon percentage, hardening increases. Next is process is heat treatment process, that is called quenching. So we have to do hardening process. That process is called quenching medium. By doing the faster cooling, or we have how faster we have to cool, that is called greater the hardness we have to achieve. And next is the factors affect the specimen size. To increase the specimen size decreases the hardness. As we have to increase the size of the specimen, the resulting hardness is decreased. So next is other factors are also affect the geometry of the parts, quenching medium, degree of agitation, surface conditions, and alloy elements. These are the factors that affect the hardness. Next is tempering process. Tempering heat treatment process. As you can see, in the tempering process, we have to, main objective is to improve the toughness of the material. Improve the toughness of the material. So there is a heating of the material, then cooling, we transform the material, then martensite, then tempering, temperature, and then cool down. So you can see this is temperature versus time. How we have to do tempering process. So we have to see the microstructure of different compositions, like martensite, how it is look like, what is the we have to get the in the marten, we have to see the microstructure of the martensite, microstructure, tempered martensite and heavily tempered martensite. So tempering is then martensite is formed. So in the hardening process, my martensite structure is formed. So further use, we have to improve the toughness of the material. So martensite formed in the hardening process is converted into tempered martensite to improve the ductility and toughness of the material. Main objective is to improve the ductility, toughness, to reduce the hardness, to remove the internal stresses resulting due to rapid cooling. In the previous topic, in the hardening process, that internal stresses stored in the material, so remove that. We have to do tempering process and to impart the wear resistance. So this is the objective of the tempering process. How we have to do the tempering heat treatment process? Heating is done 250 to 650 degrees centigrade. Steel, heating of the steel at the temperature from 250 degrees centigrade to 650 degrees centigrade, and cool slowly at the room temperature. This is also done to relieve the internal stresses. Martensite, tempered martensite, it converts martensite into tempered martensite. BCT into super saturated carbon, TM, stable ferrite and cementite, and hardness decreases with increasing the temperature. Types of tempering. So if you have to see, there is range 250 to 650 degrees centigrade. So in the different temperature range, we have to achieve different tempering process, and that have different objectives we have to achieve. So first is low temperature tempering. It is from 150 to 250 degrees centigrade. It retains the hard martensite and relieve the internal stresses. Next is medium temperature tempering. It is from temperature 350 to 450 degrees centigrade. It increases the endurance limit and elastic limit of the material. It is used mainly for spring steels. And high temperature tempering. It is from 5 degrees centigrade to 650 degrees centigrade. It relieves the internal stresses on the microstructural, mainly used for structural steels. So this is the time temperature transformation of hydroxide steel. So TTT diagram. Simply we have said TTT diagram. Time temperature transformation. So you can see this is the temperature, this is the time, and we have to for different microstructure and composition, how we have to find out the different microstructure by heating and cooling, how that time and temperature transformation occur in the eutectoid steel, we can see. So this is austenite. This there is two lines. This is two lines in between. Transformation is done for particular time, temperature of the microstructure of the steel. Next is time from temperature diagram showing the temperature in degrees centigrade, and there is time in seconds. So this will help us to how much long time is needed for particular composition of the material to transform the one property of material to another at different temperature range and composition time required. So TTT diagram helps us. It is also called time temperature transformation diagram or isothermal transformation. For that is isothermal means fixed temperature transformation. It is also called S curve, C curve, or Baines curve. It creates three processes: austenizing, isothermal heat treatment, quenching. Simply isothermal transformation. From 723 degrees centigrade to 550 degrees centigrade, perlite is formed. Transformation temperature decreases, perlite changes from coarse to fine. Means if the transformation temperature decreases, perlite changes from coarse to fine. On rapid quenching, martensite is formed, and 550 degrees centigrade to 250 degrees centigrade. From 550 degrees centigrade to 250 degrees, benite is formed. Benite is non-laminar eutectoid steel structure. Next is benite. What is upper benite is formed 550 degrees centigrade to 350 degrees centigrade, has large rod-like cementite regions, and lower benite 350 to 250 degrees centigrade has much finer cementite particles. So possible transformation: austenite, slow cooling, perlite, moderate cooling, benite, and rapid quenching, martensite is formed. So this is how we have to transform microstructure of austenite, steel austenite, in perlite, benite, and martensite. So you can do if you have to do slow cooling, perlite is formed; moderate cooling, benite is formed; and rapid quenching, martensite is formed. And this shows the properties, strength, and ductility of different microstructure. If we have to do for martensite, reheating, tempering process is done. Tempered martensite is formed. Next is CCT diagram, continuous cooling transformation diagram. So continuous cooling transformation diagram help us to show the isothermal diagram, continuous transformation diagram, which tell us what are the temperature required for particular fixed temperature or critical temperature is required for doing that particular transformations. So as you can see, this is a temperature in degree centigrade or degree Fahrenheit. Sorry. So you can see in the continuous cooling transformation diagram. So continuous cooling transformation diagram shows the time required for reaction to start and in the delay. Is what are the transformation time is required to start the reaction and in the delayed. The isothermal curves are shifted to longer times and lower temperature. No transformation below the 450 degrees centigrade. So as the diagram suggests, shows these transformations. Start of the transformation, end of the transformation, like water for hardening, normalizing, annealing, and tempering. So these diagrams are critical CCT diagram for ductile steel. In the continuous cooling transformation from martensite to perlite takes place at the range of temperature, start and finish line shifted to longer time, no transformation below 450 degrees centigrade. So these are the points. A stands for coarse perlite, B stands for fine perlite, C stands for martensite and martensite and perlite. Split transformation, D stands for martensite and E stands for point E tangent to nose of CCT diagram. Or critical cooling rate, 100% martensite. Here is you can see in the diagram. Next is hardenability. Hardenability in a ferrous alloy, the property that determines the depth and distribution of hardness induced by quenching from elevated temperature. So hardness and how much depth it is hardness is we have to achieve, that is called hardenability of the material. So hardenability versus hardness. Hardness is function of only carbon content, and hardenability is carbon and alloy content, grain size, component size, and quenchant. So what is important in quenched and tempered? Importance is optimum properties. Fully martensite steel must be quenched rapidly. The effectiveness of the quenching will be depend upon the primarily two factors: geometry of the specimen and composition of the steel. Also the austenite grain size, previous structure, types and method of the quenching. So how we have to do hardenability? There is a Gemini hardenability quenching test. So steel sample size 25 mm dia to 100 mm long, and heating the test piece to the austenizing temperature and quenching from 1 in with the control and standardized jet of water. Take the sample from the furnace and place it into the Gemini test fixtures and observe the cooling pattern. The cooling rate along the Gemini test specimen varies from 225 degrees centigrade per second to 2 degrees centigrade per second. After the quenching and hardness profile is measured. After quenching, the hardness Profile is measured at 0.1 mm intervals from the quenched end after the surface has been ground back to remove any effect of decarbonization. Means 0.3 mm is removed from the surface. Next is hardness variation along the test surface is result of microstructural variation which arises since the cooling rate decreases with the distance from the quenched. Measure the distance from the quenched end at the where hardness is equal to 54 HRC in the units of 0.1 mm. So this is the how we have to perform geminate hardenability test. Relationship between the Gemini distance and the critical diameter for an ideal quenched medium. So ideal critical diameter and distance in units, Gemini bar. Factor affecting the hardenability, austenite grain size and effect of composition. Like in the austenite grain size, more austenite grains on the surface, easier it is for the perlite from rather than martensite. Smaller grain size, lower hardenability. Smaller the grain size, lower hardenability. Larger grain size, higher hardenability. Effect of the composition, increasing the carbon percentage, increase the hardenability. Generally, other alloy additions increases also hardenability. Like some exceptions are there if there is sulfur because of MNSS and cobalt titanium. This is the Osh tempering diagram. This is the Mar tempering diagram. Next is induction hardening. So induction hardening is done by inductive current. Material is placed between the coil and the current is passed in, so that when current is passed from the coil, that induction effect is generated, and that will result the increase in temperature of the material. That will generate the heat. So induced ED current heat the surface of the steel very quickly, and it is quickly followed by jets of water to quench the component. So this process is very useful for the industries where production rate is higher required. We have to do the induction hardening process because it is very quickly controlled and operated. The hard outer layer is created with a soft core. The sideways on the lathe are induction hardened. If you see the lathe slideways, that is induction. We have to do induction hardening. So it is also called sometimes case hardening process. One of the case hardening processes is inside in which the inside core is softer or tough, and outer layer of the material outer surface is hard. That is called case hardening, and one of the that processes we have to do with the help of induction hardening. Next is another process is flame hardening. So that is we have to do with the help of gas flames, rises the temperature. So there is a gas flame that heat the material component, and then jet of water quenching the components. So this is all about heat treatment process in which we have to do heat treatment of the material and changing the or altering the material properties of the material, mechanical properties of the material from one properties to another properties by different heat treatment processes. Hope you will understand this. Thank you very much.